Hey, how's it going? My name is Keith Clark, and today I'll be explaining the cost function. We're going to be looking at a Jupyter Notebook, and we're going to be using that to understand what the cost function of a linear regression is, how it works, and I'll be showing you how I visualized it using this tool here. If you're new to this series or want to know more about what the cost function is or want to know more about what the linear regression is, I explained that in some of the previous videos for this series. I also have a study session that I recorded where you can code along with me, you can study along with me as I work through some of this material. So without further ado, let's go ahead and jump in. I won't be doing a whole lot of explaining of this topic since I did explain it in previous videos. The purpose of this video though is just to kind of go over how I was able to visualize the cost function and analyze a simple data set, basically using matplotlib inside of Jupyter Notebook. Okay, so basically the cost function, as I previously described in the prior videos, it's a way of determining what the best parameters for your weight and your bias are. And inside of a linear regression function, we have to determine a weight and a bias, which is going to roughly translate into the accuracy or the integrity of our line as it relates to the data set that we have. And cost function is just a way that we can analyze to figure out what those best weights and balances are. So to get started with this in Jupyter Notebook, we need a couple of dependencies here. These dependencies here will allow us to create our data structure, which in this case is going to be an array, a couple of arrays actually. It'll also allow us to create interactive visualizations. If you're planning on following along, just know that for a couple of these entries here, this widget and also this lab utils, these are files that you'll have to have. The course for this is in the description, by the way. It's a Coursera course that's sponsored by Deep Learning at Stanford. If you decide to create your own Jupyter Notebook based on their labs, all you have to do is look at the files, the associated files for this notebook in that course, and you should be able to get these files there, as well as this style sheet for matplotlib. So our problem statement's pretty simple. Basically what we'll be doing is we'll be looking at housing data, just very simply, and we'll be correlating housing square footage into the value of the house. And these numbers here, they seem small, but these are actually divided by 1,000. So you can think of it like this X training data is 1,000 and 2,000, and this Y training data is 300,000 and 500,000. So that means that for a 1,000 square foot house, the price is going to be $300,000, and for a 2,000 square foot house, the price of that house is going to be $500,000. One thing to know here for the purpose of this little tutorial is that cost and price, I'm using them in very specific ways, so don't get confused. The price of the house is the actual dollar amount that house is worth in relationship to its square footage, whereas I'm using the term cost here as a way to describe the summation of the errors for the entirety of the data set squared. And that will be something that we're going to work out in code, so don't worry. But this here is the formula for a cost function. I also have that formula written here, which I can make a little bit larger for you. This formula here, this J with the parentheses and a W, it might also be J with the parentheses and a W and a B. The W, remember, stands for weight, and the B stands for bias. This specific formula here is only considering the weight as a parameter, but likewise it can be written with the B, as in this example right here, where the bias is also considered. So you can go either direction depending. There might be times when you have a bias that is fixed at 0, in which case you don't need to represent it in your formula. So we're going to So what we're going to be doing is we're going to be translating this formula here into code. Another way to think about this formula here is to understand that this formula takes in, as an input, it takes in some information from the linear regression function. So when you see this function considering the weight and the bias of x at an index minus y at an index squared, just know that this here represents this here. So you see where it says the function of x at the index, it's the same as this. And the function for linear regression is the weight times some x plus the bias. So this is like a shorthand way of representing this formula here. And that's kind of what's in my notes here. So the function of x at some index with the weight and bias is our prediction for examples, for some example at an index within our data set using the parameters. And then when you see this x at an index minus y at an index, this y here, this is our actual prediction. So to kind of make this more simple, this is the kind of thing about math is like very very indirect with the notation. But even though this represents the formula for linear regression, this also represents the y hat. In mathematics, or at least in this mathematics, y hat can be thought of as the output of the model, whereas a regular y can be thought of as the input. And so basically the purpose of this cost function is to look at the difference between the output of our model in comparison to the y training set data, and then to see how different those two values are, squared of course, and it's going to tell us over the course of looking at the entire data set how accurately our linear regression line matches our data set. That's a lot to think about. But hopefully it'll make more sense when we get in the code. I think the code is much easier to understand than the math notation here. Okay, so this language that we're doing this in is Python, of course. And there are going to be a couple things that are different in the Python versus the math notation here. And so I have some notes here that kind of explain a little bit of what's going on in here. So this is very abstract in comparison to what you might do for other types of coding. So when you see f_wb, just remember that this represents the linear regression function. This f stands for function, wb are the parameters of that function. So f_wb, this underscore, if you were to put this underscore in LaTeX, which is the language that you use to create this math notation, this underscore would basically translate to this here. Maybe I can zoom in a little bit. We can look at this here. Actually, it's not a good example. I'll just have to zoom in, I guess. When you see like an underscore, like this here in a programming language, or at least in this context, just remember that that is like a way to describe this here. So like F being our letter, and then the underscore representing these two subscripts. Okay, so in our function here, f_wb represents the function of our linear regression with the weight and the bias as its parameters. And this function, whatever it provides us, is going to be the actual prediction that is made with our model. And this is not going to be its own function, rather it's just going to be something that evaluates out to some arithmetic in this case, since our code is pretty simple. And then just remember that the difference between the target and the prediction, the target is the output of the the data set. So remember that we have it when we're training a model, we have an input and we have a target. The target represents the y output. Here, let me bring up my notes here so you can see. And I always get this confused between the y and the y hat. So I'm just going to pull it up here so you can see it, and also so I don't tell you the wrong thing. Okay, so whenever you see like this y, just remember that this y is the same thing as the function of our weight and the bias considering x, or with x as an input. So when you see here f underscore wb, whatever this comes out to, this is going to be the output of our training set, which is going to be our target. And then whenever you run this method again, like if you were to take this model here and then you were actually to create it and then run some like new input that isn't necessarily represented in your data, you would get something called a y hat as the output, which is different from the target. The target is like explicit expectation, whereas the y hat is just an output that is like our prediction. And for this, we're only concerned about just looking at the target, not the actual prediction. That's not what we're doing here. So I'm going to make a quick note here, just for edification purposes. So f underscore wb, aka the target of some x at an index. Last thing too is when you see like this, I think I explained this in a previous video, but when you see like x with what looks like an exponent that has an I in it like this, or even the y here as well, this is not an exponent. This is actually representing an index within some set. And the way that looks like in code is that's just an index of an array. So here, since this is going to be a loop, we have an index of x values, and this is just going to be one of those within that array. Okay, so let's start at the top here and look at our function for computing the cost of our linear regression line in relationship to our data set here. So when we compute the cost, we have 4 different variables, or arguments rather, that this function takes in. This x represents the entire data set for all of the x values that we are inputting into our algorithm. And the y represents the entire data set for the targets that we're inputting, that we're expecting to be on the other side of this algorithm. With training, we give it, but with supervised learning, rather, we give it a set of x's, and then we give it a set of y's, and those two have to be the same size and they correlate to one another, so that any index at x has the target of some y at the same index within the y array. So that's what basically it says here. And then this weight and bias is what w and b mean. These are the model parameters. Those parameters can also be called coefficients, and that's the weight and the bias. The weight represents the slope of our regression line, and the bias represents the y-intercept of our regression line. The whole purpose of this function to compute the cost is to give us a floating number, and this floating number is the squared summation of the difference between the target value and the prediction divided by some number. In most cases, it's going to be 2m, or it can just be m. This m represents the length of our data set. And in this case, we're just going to use the x training data, the length of that, to get this value here. We don't have to do both the x and the y because they're going to be the same length. So if in this case here, the length of this x training data is going to be 2. So we're going to take this formula here and we're going to divide the value that we get from running all this summation here, and we're going to divide it by 4, essentially. And that's what we're doing right here. So next part of this function here is M, is the size of the X training data array. This 0 here is necessary because we're using NumPy, which is this dependency. NumPy is what we're using to create the array that stores our data. And this method shape is going to return for us a number which represents the length. NumPy's array is meant to also work with multi-dimensional arrays. So we use this 0 just to indicate that this array that we're working with, we want to have the first dimension of it. Although there could be other dimensions of this array, but that's like more complicated. Another way you could do this is by using the length function that's built into Python. So this cost sum here is, the way we're going to do this is we're going to basically create a variable that stores all of our iterations, or adds all of our iterations into it. And this is the way that we're going to hold the value of this summation operation. So cost underscore sum is going to start at 0, and then every time this loop runs, we're going to basically increase the value of this cost underscore sum in order to add that the value of that iteration to it. So for every index within the range of the size of our X training data, so what that means is like our X training data is an array that looks like, I'll just go ahead and copy it down there. So our X training data is going to look like this, right? Yeah, our X training is going to look like this, right? And it's saying that the size of this array matters because we're going to do a looping action over every index of this array. So if this data set was five items, it would be 5 times. If it was 20 items, 20 times, whatever the size of this X is going to be. So we're going to loop over that. Then we're going to run our linear regression function to derive a line from this, from every index of this array. So we're going to first start with 1, and then we're going to do this with 2. Every time you see this X with the square brackets and an I, that represents the current index of this iteration along this array. We're going to multiply that, whatever that value of that index is, by the weight, and we're going to add the bias to it. That's what a linear regression is essentially doing. That's the formula for creating a sloped line that has a y-intercept of some value. To calculate the cost is, remember this part up here? Yeah, this part right here. A simpler way to think about this formula, because I know this is a lot, I prefer to kind of look at it like, find it here. I close the document. Oops. This one. Another way to think about it is like, I prefer to look at it this way. Let me change my view here too, so it's like, this will stop giving me that latex stuff. Okay, so if you see here, this y hat of an index and this y of an index, that's what this represents here. So this first y hat of an index, this is the actual, actual linear regression function. And then this here is the actual, so this is the training data basically, and then this is the prediction that's made from the model. And another way to think about it here is, this is the error. So you see how this here, this is just the error. The error measures how far the prediction is from the target. I'm gonna show you a visualization of that toward the end, so it'll make a little bit more sense. So we're gonna run this linear regression function here. We're gonna call it, and it's going to be using whatever the current indexed value is for that X training data, and then it's going to subtract whatever the value is from the Y. One thing you should assume when you're running this compute cost function is that we have already provided it our targets. The targets are like the expected values, whereas the linear regression function here, that's like the modeled values, like the predictions, I guess. So we're going to be subtracting the expected values, the targets, from the predictions. Then we're going to take that and then we're going to square the value of this. So all of this here represents one index. We're going to take that calculation here and we're going to square the entire thing. Star star in Python is just a shorthand way to say square a number. And then, like I mentioned before, this cost sum is going to hold the summation value for the entirety of our loop. And we're just basically here going to add to our summation, to our cost sum, the cost that is calculated from doing this math here. We're going to take the total after this loop runs over all of the indexes for our X training data. Then we're going to take the total of that and we're going to divide it by 2 times the length of that X training data. Remember, M is the length or the size of that training data, which in this case is going to be 2. So 1 over 2 times 2 is like 1 over 4. So we're going to take the cost summation and we're going to divide it by 4 essentially, and that's going to give us a number. Okay, so let's take a look at some illustrations, some graphical representations of this. This will make it a little bit easier to understand. So our goal is to find a linear regression model with some unknown parameters, and these parameters need to accurately predict the value of some given input. Like if we were to take our model and provide it some number that doesn't get represented in our training data, we should be able to like come up with an output of our model that gives us some guess that is aligned as closely as possible with the general trend of our data set that we've trained our model on. And the real key to linear regression is how the weight and the bias affects the model. So that's what the squared cost function is doing, error cost function is doing. Don't look at this. This is part of the answer, but the whole purpose with running this function, by the way, is that we're trying to make sure that whatever number comes out on the end of this is the lowest possible. And the closer that this number that is the result of this summation and division, the summation, squaring, and division is, the lower that number is, then that means the more accurate our data set is. The more accurate our prediction is, rather, in comparison to our trained data set. And it's not always possible to have our cost at 0. The more data you have and the more irregular that data is, then the more difficult it's going to be to fit a regression line. And then also some data could have a pattern, but simply may not follow along a straight line, a linear line. So linear regression isn't always the best option, but when you do use it, getting that lowest cost is going to give you a higher accuracy for your predictions. At least it'll let you know how reliable your predictions are. For this particular training set here, I already know what the weight and the bias should be, but we're going to take a look at what happens when you toggle different values for the weight, and I'm going to describe for you what this means with the graphic representation. One thing to know though is that there is a way that you can actually calculate the best bias and weight. That doesn't require you to sit there and like punch in different numbers for each of them. The intuition part of it though is quite important. So something I said a little bit earlier is that the weight and the bias is going to have different influence over the kind of line that gets created on your plot here. The weight is going to determine what the slope of your line is, so like how diagonal. When your weight is 0, the line's going to be like flat, and then the higher that weight is, the more that line is going to reach verticality. The bias is the y-intercept. Remember, y-intercept is the point at which your line crosses the y-axis from its origin. So if this line, for example, was like if it was still the same angle here, but it was moved up, that means that the bias is higher. Okay, so this toggle here, oh, by the way, this PLT underscore intuition, this is a method that comes from this dependency here, this lab utils uni. So this is not going to work just using like vanilla Python, although there is a like a file that is provided if you do take this course that you can use to run this, but there's like some code that's happening that is not necessarily apparent. I'm going to take a quick look at that just to show you what that code is doing, just for your clarification. So I'm going to open this up here. I'm going to go down to this here. Okay, I'm going to go down here. Intuition. I'm not going to read all of this for you, but the main thing I want to show you is that for this graphic representation, we're only at this moment concerned with the weight. The bias here is fixed at 100, and the way that's being done in the code here is in this line 69 here. And then all of this code here is basically just what's allowing us to generate this graphic representation. So don't worry so much if you try to do this and you're like, oh, you're only putting in the W, the weight. Under the hood with this specific thing I'm doing here, this is setting the bias for us. Okay, so let's take a look at what happens when we change the value of our weight. And remember, the weight is going to be concerned with the slope of our line. So as we increase this, we should see our slope becomes more dramatic, right? Remember, before our slope was actually aligned with our point here, but now it's not. And if I move it lower, we should see, oops, it's a little buggy. Okay, we move it lower and now our slope is like more flattened. You see that? Okay, so now if you look at this, right, one thing you can see is that there's these little dots here, these little dashed lines, and then you have these red dots. On this graph, the red X's actually, these represent the actual values. So when we put our training data in, we have a set of X and Y values. The X's represent the size of a house and the Y's represent the price of the house. The X's represent the inputs and the Y's represent the training data for the output that correlates to those inputs. These X's represent what we know for sure as we're training our data. So we know that at 1,000 square feet, this house is going to be $300,000, and at 2,000 square feet, this house is going to be $500,000, and that's what we see when we look here, right? So X, Y, the first index of the X is X of 0, and then the first index of let me stop. The 0th index of our X training data, that is the X coordinate for the first dot, and then the 0th index of this Y, it is the Y coordinate. So when you see here, the number of the index for each of these two arrays, it's like a pair. They're paired together. Let me show you really quickly another way you could represent this. This is not how you would do it, but this is another way to think about it if it's kind of confusing. So you could say like training data equals, I'm not going to use NumPy. This is actually just going to be, I'm going to delete this after I show you. So this could be represented as a multi-dimensional array where we couple our x, y values instead of putting them on separate arrays. Position 500. Right? So just think about it like when you see this x training and this y training being separated, just remember that the way that we actually use them to represent points on a plot is in a coupled way. Even though they're considered to be separate columns, they're coupled data. It's just that the first index of each of these couplings, or the 0th index of each of these couplings rather, represents the x, and the first one, zero index programming languages are confusing. Let me just pause and say that. It's not confusing inside your head when you get used to it, but it's confusing when you talk about it. Okay, let me start over. So the 0th index of this array, of this 0th array, this represents the x coordinates, and then this one represents the y coordinates. So these are coupled. Another way to think about this is to look at a data table, by the way, and that's what I have here. And you can see these rows and these columns. The columns represent the x's, and the here represent the x's, and this column represents the y's, and then the rows represent the pairs, the xy pairs, which you could also call vectors, I guess. Okay, so let me get rid of that and go back to our diagram here. So the next thing to think about when you're looking at this diagram, this representation, is you see how there's like a dashed line. This dashed line is connecting our actual values that we're plotting out based on our training data, and it's drawing a line from that to our prediction. This prediction here, this line here, the way to think about this is the actual regression line that we have created based on the weights and the biases that we're using for, running this. So as we change the weight, as we change the weight of this, then the slope changes, and this regression line is going to move either toward or away from our actual values. The dashed line here is like a visual way to represent how closely, or like what the difference is between the actual values and our prediction. So the smaller this dashed line is, and the better our model is at making these predictions, the closer our regression line is to our actual data. On the right side here, you see this parabola, this upside down U-shaped parabola curve. And earlier I was talking about how with this function, this squared error cost function, when you run this, here's another one. When you run this function here, your goal is to get a minimized value for the cost of whether or not you're doing this with the weight or with the weight and the bias. In this example that I'm hovering over, this is just the weight, so this is the same formula we're using for this down here essentially. But regardless of whether you do the weight and the bias or one of them alone, this minimized j, what this means is that we want to get the lowest number we can when we run this function here. And so on this graph here, this plot rather, the lowest value for cost is going to be represented at the lowest end of this parabola. So right now you can see that our weight is at 260, and so therefore our parabola has a point at it that is, the cost is 260, or no. The cost is 4,500. That means that the difference between the summations of all of our predictions and our actual values squared, and then divided by 4 is going to give us this level of accuracy. Now, if I know that I know that the bias is set to 100. We looked at the code a couple seconds ago. And I know that when we set this weight to 200, that when we do that, this cost will actually be at the most bottom end of this curve, which will be, it'll be horizontal to this 0, which means that the cost is 0. So that's my guess. I'm gonna do that and we're gonna see that happen here. This thing is glitchy. Okay, there it goes. It's so glitchy, sorry. If I was running this in like another app, I think it'd be smoother, but just forgive me. Okay. So now that we've set this to the correct weight, which I already knew, you can see here that this horizontal line is going to match it up exactly with this 0, meaning our current cost is 0 here. And the cost here, like I said, it's going to be on some position along this parabola. By the way, this parabola is non-linear, and the reason why it's non-linear is because when you're multiplying, things don't increase like in a linear way. When you're doing multiplication and addition as coefficients to something, it's not going to increase linearly. So, you know, the more you move this weight, if you know higher or lower, it's not going to increase the cost in a linear way. It's going to be non-linear. Okay, so things worth remembering is that the cost is minimized for this example when the weight is 200. The cost increases rapidly when the weight is either too large or small. That's nonlinear progression along this parabola. And then when you're using the weight and the bias, we want to basically minimize the cost, and that's going to give us the most effective prediction. And this is in order to calibrate, so that if we were able to make a model and we wanted to ship it off, you know, send it somewhere else, and then just have a level of trust that it can do what we want it to do, we don't have to like package all of this training data with it. All we have to do is just have the model and have it calibrated with the right weight and bias, and then we know that it's going to give us a certain level of accuracy. And also, the more data you have, and also the more complicated your regression formula is, because there are other regressions outside of linear, then the more reliable your method, your function is going to be. But that's something we'll get to later on. Okay, so we're going to do this now with a larger set of data. And the one thing to know about this larger set of data is that even though there are more points and that they do follow a general trend, these are not going to follow along a convenient line like we have here. These will actually have some data points that cannot be perfectly lined up. This is more typical for like normal situations. And when you see that the points cannot be lined up like this, something you could assume, if this was like a realistic example, is that perhaps there are other variables that play into this data, which we'll be able to handle in future videos. Okay, so this is our training data, similar to what we did before, just instead of having 2 entries, we have 6 here for each of these arrays. All this stuff here, this is, once again, this is just stuff that's coming from some like background code that you don't have to worry about so much. I'll try to make that available. No promises, no guarantees, but I'm going to publish my notes in a blog, and when I do, I'll potentially have some links in there if you want to do this in your own environment. Otherwise, you can just check out the course. So with this new set of data here, we basically did the same thing we did before. We plotted out a regression line that is attempting to match our data as closely as possible. Here it's just being done for us. The big thing here is that we can see that this line here is going to change, and we can actually use this interactable chart or plot here to move this around. Now let me pull up some notes here so you can kind of understand what's going on here. So before, in this example here, we were plotting out the cost using just like a 2D parabola to represent just the weight. Now what we're doing is a little bit more complicated. We're actually doing 2 different things here. This first one on the right side, this is called a contour plot, and this bottom one here is called a 3D surface plot. The 3D surface plot, as you can see here in the notes, This 3D surface plot has 3 axi. It has a weight along the y-axis. It has the bias along the z-axis, and then it has the function for the cost function along the x-axis. And this color shift that you see here is actually called the gradient descent. Within this, what we call a soup bowl, this gradient descent, as it goes down and it reaches like this blue section here, this blue section represents a lower point, and this warmer colored red section represents a higher point. As you move down, just like in our 2D representation of the weight, the cost in relationship to the weight here, the further you get down to the bottom of this visualization, that represents like a lower cost. So here you can see in this here, this weight, I can move this around here. Whatever this blue section is, whatever part of that blue section is the lowest on our graph here, you can see if I move it like this. Whatever point here, whatever the coordinates are for whatever point is the lowest here, this is going to be the lowest cost for our training data. And you can see here, if I change, oh, by the way, in this plot here, when I'm moving my dot around, this is actually just changing the weight and the bias. So when I move it along the y-axis here, when I move it along the x-axis here, it's changing the weight. When I move along the y-axis here, it's changing the bias. So I'm gonna move it really far out to the side, right? And you can see here that it's really far away from the base of this plane, and subsequently the cost is really, really high. And you can see here that the difference between our regression line and our training data is like really big, right? By the way, you can see every point on this training data has a number assigned to it. These are the numbers that we're adding together, squaring, and then dividing by 2m, and that total number is how we're getting this cost, by the way. So this contour plot, it's a little bit confusing. One way to think about this is like if you look at like a contour map, I think I have an example here. If you're looking at a contour map, think about like how contour maps usually represent like the altitude of a mountain, or the way like a terrain is, if you've ever seen like a contour map. Well, that's the same thing here, except it's kind of like in the inverse. So as you move towards the center, this value for cost will get smaller, right? And then as you move towards the outside, it'll get larger, right? So whatever is at the center of this is going to represent the lowest cost. Now with this data, remember, our cost cannot be 0 because these training data scatter points, these are not aligned perfectly. So we just are attempting to get the lowest value possible, closest to 0 possible, and that's what our minimum is. So our minimum for this is probably going to be somewhere around 1,700, somewhere in that region. Sidebar, as you use like more complicated models and algorithms for representing your model on your plot and stuff, you can actually have multiple minimals, and that'll be like kind of a topic we explore when we get to gradient descent. You can have multiple minimums, and you can have like what are called local minima for really complicated sets of data that we're modeling. But just stay tuned, we'll talk about that a little later. Okay, so moving on to this last example here. Nothing to graph here, but this is just going to basically allow you to see like this surface here, this soup bowl. It can also be called the error surface. See, it's error surface, and this is probably a little bit easier to like to kind of see where the minimum is, because it's going to be at this lowest point here. With both this and the parabola that we have on line 4 here, there's always going to be some symmetry. So there are other types of gradients that you have, but for linear regression, it's going to be this like symmetrical type of supple plane. I just think that this looks so cool. I would definitely like buy a t-shirt with this on it for sure. That would be so fetch. Okay, so that's basically it. This is like a big topic. Don't worry if you didn't get it all today. I have had to look at this many times and I still get it weird. The nice thing about it is, like, when you're doing code and stuff, a lot of these are things that are like in pre-made packages, so you don't always have to necessarily do this manually. But for learning purposes, what I would recommend is to just play around with this yourself, and to go through all these steps. And like I said, the course for this is mentioned in the description of this video, and I would highly recommend taking it. It's a great course. This is part of their supervised learning course. So anyways, thanks for checking out. I'll catch you later. Stay tuned. Don't forget to follow, like, subscribe, comment, do all that stuff. I have links in the description if you want to check out my LinkedIn or any of my other stuff. I do a lot of things. My name's Key. Peace.